Okay, today we will discuss about Carnot cycle, its efficiency, and some concept of entropy. Okay. And tomorrow we will discuss about Clapeyron equation. It is a change in temperature with respect to pressure. Okay. A change in pressure with respect to temperature. Dot P by dot T. And then we'll go for the partial molar quantities. Maybe for first MSc students, I'm not sure whether you read in your BSc or first MSc the partial molar quantities or not. So these are applicable to open systems because you know that when but we have discussed three different kind of systems. In that, one is open, second closed, and the isolated system. In the last two systems, closed or isolated systems, the matter cannot be exchanged with the surroundings. Whereas in the open system, matter can be exchangeable. That means the quantity of your material, whatever it is, whether it is a gas or a liquid or something. So when you heat it, some amount of the material is exchanged to the surroundings. That means there is a change in the number of moles as well. So far, whatever we are discussing, we never discussed that the change in number of moles. We always assumed that the in the system the number of moles, the amount, the quantity of the material is constant. Okay. So from tomorrow, from that when it comes to the partial molar quantities, it is an open system. When you are an open system, you always have a chance for the number of moles, the quantity of the material to be changed. Okay, that is the only way. That is where we discuss about the partial molar quantities and the corresponding Gibbs dual equation. So today, majorly I will discuss about the entropy only. We already have a some extent of idea about the entropy and in what conditions the spontaneity comes. Okay, when you are discussing about the thermodynamics itself, the application of thermodynamics is it can give you the spontaneity of a process, whether your my slides visible or not.
Visible, sir.
Visible, sir.
Uh, So the main application of your thermodynamics is it can give you an idea about the spontaneity of a process. Okay. So in the first law of thermodynamics, we majorly discuss about the free energy. Uh, Depending upon based on the free energy values, we are discussing, we are trying to establish or we are trying to decide whether a process or a reaction is spontaneous or not. And you know, we have already discussed that part that and that when you want to discuss in terms of internal energy, you have to keep two variables that are constant, that is entropy and volume. Okay, so volume you can keep constant by taking a specific vessel or something, but entropy there is no measure of keeping it constant. So in that sense, it is not so much useful for us to discuss in terms of internal energy whether a process or a reaction is spontaneous or not. Okay, so majorly that is the reason why the second law of thermodynamics has introduced new state function known as entropy. Okay, so entropy is in molecular perspective, entropy is a measure of disorderness of a system. So in thermodynamic point of view, the definition of entropy is the change in entropy you can measure based by measuring the amount of heat transferred upon temperature. Okay, ds, the change in entropy is dq reversible by temperature. Whenever you are speaking, always remember that you are always speaking about the change. Okay, absolute entropy we are not talking at all. Absolute entropy also you can it is under, you will learn this one, but this will be, this is taught to you at the microscopic level, you know. So whatever we are dealing now is macroscopic level. Even macroscopic level in the sense that when you are considering a system, it is a matter of the system consists of several number of moles of molecules. Okay, so several number of moles of molecules are some hundreds of molecules, several molecules you are dealing about. Okay? That is called macroscopic system. So when we speak about macroscopic system, we cannot determine absolute entropy of the molecule, because in each molecule there are changes in the entropy, and even in one molecule itself, based upon its electronic arrangements, there are changes that happen in one molecule. The entropy changes. Okay. So those, if you want to determine absolute entropy, you can only go through the microscopic system. Microscopic state is nothing but, suppose in terms of the system, if you want to consider other than n number of moles, you are going to the one molecule. Inside one molecule, how your the microscopic particles, that neutron, proton, or the electronic arrangements are there, and their contribution for the entropy. That is called as absolute entropy. That is given by, it will be taught to you in statistical thermodynamics. Okay, statistical thermodynamics is nothing but thermodynamics at microscopic level. You are giving quantum mechanical treatment to the thermodynamics. Okay, you are trying to understand thermodynamics through microscopic properties. That is called, this is K log W. Here, based upon the number of arrangement of the atoms in the molecule, we will learn the entropy. That is called absolute entropy. But whatever we discuss in thermodynamics, here we only discuss about the change in entropy. Okay, depending upon the change in entropy, we are trying to conclude whether a reaction is spontaneous or not. Okay. This is the thermodynamic definition for the entropy, the amount of energy supplied based upon temperature. Okay, you know that entropy is a state function. So for a state function, you can establish a definite integral for that. So a definite integral in the sense that you can clearly measure the change in entropy, delta S. So delta S will be the change from initial state to the final state. Here we come to the point that dq reversible, q reversible here is the, suppose in terms of isothermal expansion of the gases, the amount of energy supplied or released depending upon the process you can consider. So if it is an expansion, for a isothermal process, the energy is supplied from outside of the system to the inside, okay, to maintain the thermodynamic thermal temperature, same temperature. We have discussed this one already. When the system do some work, it spends some amount of internal energy. So there is a drop in temperature. To compensate that one, since it is an isothermal process, system accepts some amount of temperature energy from outside. Okay. So this one is the supplied energy when it comes to the isothermal expansion. Okay, we know that Q and T, Q and W. W is the work done. Q and W are opposite to each other, because in isothermal expansion, you know from the first law of thermodynamics, dQ is equal to du plus dW. And from first law of thermodynamics, we know this du is 0 for isothermal process, because system is, suppose you have taken some system. I hope you guys remember this one. So this is a piston you have. In the final stage, you are expanding the system from here to here. There is some expansion. During the process, if the amount of energy is spent by the system, it will accept some amount of energy from the surroundings to maintain that thermal equilibrium, because the system is at isothermal conditions. So your internal energy change will be 0. So dq and dw are equal but opposite in sign. Okay, you know from the first law of the, for the isothermal expansion of an ideal gas, the work done is nRT into ln V final upon V initial. Okay, so we have, because the negative sign we took in the other way. So delta S will be nR ln V final upon V initial. This is one of the important formula when you are asked about the isothermal expansion of the ideal gas. To calculate the change in entropy, we can utilize this formula. So if you please have a note of this one. This one yesterday I uploaded first class slides and the remaining also I will upload. There is a problem with respect to the size of the presentation. Okay, so now take this problem based upon the concept that we have discussed, whether we can able to answer this or not. So B to C is B to compression. Is any answer?
Is it D, sir?
Yeah, but there is a change in temperature T2 to T3. It's not an isothermal condition. Okay. As of now, I also think the answer is D, but let's have a further detailed discussion in the next class.
Excuse me, sir.
Yes, please.
From
Uh,
just a minute, sir. Here we have to consider only B to C or considering, right?
yeah, B to C, okay.
Okay,
B.
sir. No. Okay.
Is adiabatic process. Cannot be isothermal. Usually, if you see in adiabatic process, if delta S is Q by T, Q should be 0, then entropy should be 0. Note down this problem. Okay, so we'll discuss about the Carnot cycle. If you see, yesterday as we discussed, the Carnot cycle is the combination of, so means the major idea for designing the Carnot cycle is to find the efficient engine, that maximum efficiency to extract the maximum amount of work by supplying some amount of energy. There is a Carnot is an engineer. He has designed this process that it has 4 different process that goes on in a cyclic process. Starting from A to B, it's an isothermal expansion followed by adiabatic expansion, then isothermal compression and adiabatic compression. Here we will discuss mostly about the entropy change in each process. If you see that here in isothermal process, the initial amount of energy supplied, you consider it as QH. Okay. So when it is expanding, the energy flow is from the surroundings to the system. I guess you are able to follow. I don't have the diagram here because when the system is expanding, system is doing work, so it is spending some amount of energy. When it is spending some amount of energy, the temperature of the system is dropped to maintain the isothermal condition. The system accepts energy from the surroundings, so that temperature is maintained. Okay, So QH is the amount of energy supplied to the system. Whereas when you come to the adiabatic process, remember that here it is given, right, Q by T. In adiabatic process, whether it is a compression or expansion, your amount of energy supplied is zero. Okay, so the change in entropy will be zero. Is that okay? Similarly, for the compression, you will have QC, the energy returned to the surroundings. Okay, when you do work on the system, energy of the system is raised. So the remaining energy, to maintain the thermal equilibrium, remaining energy system throws back to the surroundings. So QC is the amount of energy given back to the surroundings. And again, this is an adiabatic process. In the adiabatic process, the amount of energy that you are supplying is zero. So your entropy change here is also zero. Here is also entropy change zero. Whereas in isothermal conditions, you will have some amount of energy, some amount of change in the entropy. Okay, so that this, this is cyclic integral. That means in a cyclic process, total amount of change, it is designated as this one, and so the total amount of change in the entropy can be calculated by the sum of the entropy change in the each stage. So at this stage, the entropy change is Q upon T. Okay, Q is the supplied energy upon temperature of the system. Here the temperature is TH. Okay, you consider it as TH. And in the second stage 0, third stage you will have QC by TC, and fourth stage it is 0. And here if you go for the definite integral delta S, you know that S is a state function. Entropy is a state function. Cyclic integral of the state function is
Zero.
0.
0.
Yeah. So from that you can have this relation QH by TH is equal to minus QC by TC. So this is useful in determining the efficiency of the working engine. So efficiency is can be calculated based upon work performed by the amount of heat you are supplied to the system. Okay. From hot source, you are supplying some amount of energy to the system, to the engine or system. So the amount of work done you will calculate. The ratio will give you the efficiency. So here work performed, we know that Q and work in terms of quantitative terms, Q and W are same. No, the amount of work done will depend upon the energy supplied. Energy supplied will be the difference between the initial energy and final energy, means hot source and cold source. The difference amount of energy will be the total, the dq that you are supplying to the system, and system utilizes this amount of energy to do the work. So instead of work, we are writing what this energy is in terms of, we are writing the supplied energy, QH minus QC. Is there any doubt in this?
No, sir.
Okay, so it can be written as this one. Here, this I am writing in this form. Is there any doubt here? In previous slide, we have shown that QH by TH is equal to minus QC by TC. Okay. So now, the same thing I am writing here as this one. Any doubt? It looks confused. There is one minus sign, right? You want to write QC upon QH. it should be equal to Tc upon Th, but with a negative sign. Is that okay? From this to this.
Yes, sir.
Whereas when you
Sir.
take the modulus, it means that you are only taking the quantity. You are not bothered with this sign. That is the meaning of the quantity. Is that correct?
Yes, sir.
Yes, sir.
So, since you are taking only the quantity into consideration, it can be written as Tc by Th. Is that okay?
Okay, sir.
Right, right. So when you forget, in case in when writing exam, the formula, so you can derive the formula based upon this. It is very easy to understand that once efficiency, consider that one, the efficiency of a person or something, how it will be considered, how it can be calculated, the amount of energy that given to him to the amount of work he has given to us. Okay, like that, if you consider efficiency from this theoretical formula itself, you will be able to derive this equation. So only thing, if at all, if it confuses to you, will be here in terms of the sign. Okay, always remember that energy is in terms of quantitative aspects only we are considering, so we always take it into the modulus. You should not end up by omitting q. If you omit this modulus, you will end up in getting this one. Okay, so this will never give you the, you will always get more than 100% efficiency. Remember that there is no engine that works with 100% efficiency, even 100%. Okay, in case by chance when you are calculating in your calculation, if you are getting more than 100%, just recheck your derivation. So you have done some great mistake. Okay, if Carnot engine is the designed to, that is the most suitable design to prepare a maximum efficiency engine. Even that itself, it cannot give us the 100% efficiency of work. There is always some amount of energy lost in the form of heat. So that is the reason why you can clearly understand this one. When you are riding a bike or something, your engine gets heated up, right? Some amount of heat energy is wasted. That means that the amount of energy in terms of thermal energy, it is being transferred to the surroundings. So that energy is always wasted. So you will always get only the efficiency less than 100%. So there are often questions being asked from Carnot cycle in terms of its efficiency. So please note down these equations. So these are very useful for you in calculating the efficiency of a working engine. So then we can, when you go for the other aspect, the entropy of mixing is one of the very important aspects. This is in terms of examination. I am not deriving it anymore. I'm directly giving you the formula. Please write down this formula. This formula, only remembering this formula also can give you at least answer for some questions. We will discuss this. The derivation we are not going to discuss, only consequences and from where it got, that we can discuss. Okay? But in my understanding, that if you can remember this formula, it is good enough. Where the N is the total number of moles of the gases. Okay, this gives the total number of moles. R, this is a gas constant. Xi is the mole fraction of any one single component. Okay, so remember this formula. In textbooks, in some textbooks, it is written in different way also, that this total number of moles, if you take inside, so the formula will be different. Okay, only you fix for only one form of the equation, and probably this is one most easiest one to remember. You can remember this formula. This, I guess, this question is based on the same. You can try to attempt this question. The total number of moles are total number of moles is n is equal to 4.
4.
4.
Yeah, you can calculate and tell me the answer. Okay, if you find any difficulty in calculation, let me know. I'm not solving it now, but I will solve it later on. I don't want to. I want. Apply the formula directly. minus 4r. What is xi? X is 1 by 4. Suppose I am considering CO2 as first one. You know that, right? Sigma xi, and if you have this one, you can expand it in terms of each one. If you have 3 number of molecules, it will be x1 ln x1 plus x2 ln x2 plus x3 ln x3 ln x3. Okay. So write it in terms of this one. It will be like 1 by 4 ln 1 by 4 plus 1 by 4 ln 1 by 4 plus 2 by 4 . So now we just calculate this one. Any answer? So how you can solve this? This is a simple mathematics. You can. So first these two terms, try to mix these two terms. Ln 1 by 4, if you take comma, if you can write it as 1 by 4 plus 1 by 4 natural log of 1 by 4. Okay. This is, you are combining these two terms, and here you can write it as, you can keep it as such. Okay. 2 by 4 ln 2 by 4. What you will get from this is 2 by 4. 2 by 4 ln 1 by 4 plus 2 by 4 ln 1 2 by 4.
Sir, I have done up to that, sir.
Okay. So you don't know how to solve this. Take 2 by 4 common. Can you
Sir,
take?
ln AB.
2 by 4 you take common. You will get ln natural log of 1 by 4 plus natural log of 2 by 4. So you solve it directly. Now ln a by b, you can write it as ln a minus ln b, right? 2 by 4 you are taking it common. ln 1 minus, sorry,
Sir, can you please scroll little up?
I'll write it up. Okay. You can write this one as natural log of 1 minus natural log of 4. Is that okay? Plus natural log of 2 minus natural log of 4. Is that okay?
Okay, sir.
All you can convert into in terms of ln2, right? So ln1 you can natural log of 1 you can omit it as you can if you go for nat 10 base 10 2.303 log 1 you can write it as, okay? Is that okay? I'm writing natural log 1 as 2.303 logarithm base 10. And this value we know as 0. Log 1 is 0, right? Any doubt in that?
Okay, sir. Yes.
So you are, so based on that I am omitting that first term. This is 0. And now convert all these in terms of natural log 2. You can write it as 2 square. Is that okay? 4 you can write it as 2 square. So it will become minus 2 natural log 2 plus natural log 2. Here again minus 2 natural log 2. Can I write it in this way? If you have, means if you are not really sure about what I am writing, you can copy it. And then brush up your basic mathematics. It is easy for you to follow them. Overall, what I got is that minus 4 natural log 2 plus 1. Okay, so I'm writing it as minus 3 natural log 2. Any doubt in this so far? If you have any doubt, you can ask me without any hesitation, okay?
Sir, from this blue written step.
From
Blue.
the
Blue.
blue.
The starting is.
Okay. So I have written, you have this one, right? ln4, right? Or else minus ln 4 you have. I'm writing 4 as 2 square. Is that okay?
Yes, sir.
So you know that if you have ln a upon b, this can be written as b natural log a. This is the formula. You remember that? Is that okay?
Yes, sir. Yes, sir.
So you write it as minus 2 natural log 2. Fine? This 2 I am bringing it in front. Is that okay?
Fine, sir.
Now you add it up. That's it, right? Minus 2 plus 1 minus 2.
6 are land 2.
6 are ln 2. Okay. From here we started, right? This is the expression for this. So what you have final answer 4r into 2 by 4 we have already into the expression for the this one in bracket it is minus 3 ln 2 and go for this minus 4 you will end up in getting 6 r ln 2. If anyone has doubt, I can explain for one last time. So one more thing I can suggest you is that some basic mathematical formulas you just keep practice once or twice. Okay. So when you are doing physical chemistry, especially if you go for quantum mechanics, you require integration. Mostly the integration very well. You don't need to go for deep integration, just the +2 mathematics, initial one or two chapters, if you have a look at, or else for the list of your formulas, if you have physical chemistry Puri Sharma Patania book, in the first chapter, you will be given the list of formulas that are useful. List of mathematical formulas that are useful in solving the quantum or the physical chemistry questions. Okay, those things you need to remember always. Those are not new to you. I know all of you must have solved all those questions. In +2 mathematics itself, you have the integration. These are simple integrations, but during the course of your past bachelor studies or masters, you might have forgot some formulas. You just have to recollect them. Okay. Here, whatever we have solved is this simple logarithmic formulas. Only two formulas we have used here. So when you have ln a plus, I guess this is the only formula that we have used here. Okay. So that with that I'm moving forward. Okay. I hope you all understand how to solve this question. Similar kind of questions you keep getting in net or gate. So if you have a collection of questions, please practice that. This one, just a recollection, this is direct formula for isothermal reversible expansion. Yeah, this is the question that we wanted to discuss yesterday also. How many of you have written the descriptive answer for this question? What you are asked is that you have an ideal gas is subjected to the reversible adiabatic expansion. The stage 1 is reversible adiabatic expansion. Then you brought back the system to the same volume through reversible isothermal expansion. So suppose this is stage 1. Just for your clarification, I indicated this in terms of this figure. The blue you can consider it as a adiabatic process, and you brought back that in isothermal way. So in adiabatic process, the amount of change in Q is 0, right? The system does not take any amount of energy, neither it takes nor it gives back. So your Q is 0 here in stage 1, and this one is expansion. So system is doing work, so the work is negative less than 0. Any doubt in this?
No, sir.
Okay. So the next stage is isothermal compression, right? When you are compressing, you are giving energy to the system. So internal energy of the system increases. To maintain the thermal equilibrium, the system throws back some amount of energy to the surroundings. Okay, so overall the process is that Q is going to be less than 0. Whatever you are giving away from the system is negative. Whatever you are taking, we are considering in terms of system. Whatever taken out from the system is negative. Whatever giving in is the positive. Since the system is giving back the heat energy, I'm considering it as Q negative, and work is done on the system, so work is positive. Now, if you want to have a total change, you need to consider the changes happened in stage 1 and stage 2 together. So if you consider in terms of Q, if you consider one is equal to 0, another one is less than 0, the combination will be less than 0. This is straightforward, isn't it? And now,
Yes, sir.
here you have two processes. One is work done less than 0 in terms of adiabatic process. In isothermal process, work done is greater than 0. So if you combine these two, the work is either what are all the possibilities? If you have adiabatic work more, then resultant will be W less than 0. If you have equal amount of work done, then the amount will be 0. If the isothermal work is more, you will have W less greater than 0. So now what will be the final answer when you are combining one negative, one positive? You are combining, the total will be positive or negative. We have discussed this point. I'm not discussing total. We have discussed it as a complete slide. Okay, today I will upload that slides to you. Please have a look at that. So in terms of work done, the reversible isothermal expansion work will be higher always. The work done in reversible isothermal process will be higher, and then followed by the reversible adiabatic process, and which is greater than the irreversible process. Always reversible work is more than the irreversible work, and in reversible work, isothermal system do more work than the adiabatic system. Okay, because in adiabatic case, in isothermal case, there is a very slight change at each stage you are maintaining equilibrium. So based on this point, now if you see this one, this is isothermal adiabatic work. I consider it as AD, okay, and this is isothermal. So this is dominating factor. When W greater than 0 is dominating, the resultant will be less in quantity, but this will always, the sign is followed for isothermal sign will be followed, so you will have W greater than 0. Is that clear?
Yes, sir.
So
Yes.
this point we have already discussed. Keep remember this point. This is one of the very important point. Okay, based on your analysis of this concept, you will keep getting questions in that. So option will be
B.
B. Okay, if anyone want to copy this one, you can copy. Whenever possible, try to represent your answer in pictorial point of view. Okay, that will strengthen your understanding. Okay, so this is the information you required for to answer this question. Now you go for this.
First is not correct, sir.
Okay.
The fourth is also not correct.
Mhm. How are you solving this? Means what is your method? What is the method that you are following?
Maxwell equation.
Okay. Did you discuss how to solve this?
By that method, Satya Prakash very talented.
Did we discuss already?
No, sir, the discussion is remaining.
I can give you one more trick. You are asking for TVS, right? Rho T by dV at S is equal to, let me try. If it works out and it is good. Yeah, try to follow this one. If you write dou T by dou V at constant entropy will be equal to dou S by dou P at constant temperature with negative sign. I'm writing this. So you are starting this arrow from here, start from here. So dou T by dou V at constant S. This will be equal to, from this wherever you end it, you start from there, dou S by dou P at constant temperature. Do you have anywhere this relation? No, right? And this will be negative sign. You can take whatever going up you take as negative, whatever going down take as positive. Now you try to solve based on this. TDS, TPS. Yeah, can we write this as negative of the reverse order? I guess we discussed that. Suppose you want to reciprocally change it. Can I write it as this one?
Yes.
Yes, sir.
So you got any? So it is same as option B. Is that okay?
No, sir. It's option C.
Option C is correct.
Yes, sir.
Okay. Dou S by dou V at constant temperature. The sign will be changed, right? Dou S by dou V at constant temperature. That means that you are going in this way. So you will start again this way, go up. So dou T by dou P at constant S. How you arrive to that point that it is correct? Option C.
Sir, in option D, there should not be negative sign in the left side.
Sorry, option D.
Sir, there should not be negative sign in the LHS.
Okay. Dou S by dou P at
That is also wrong.
You are telling that option D is wrong.
Yes, sir.
C, I don't think it is correct. I guess this one you saw this solution and B, are those matching? That's what I'm asking. Dou T by dou P, sorry, this one right? Dou T by dou P at constant entropy, which is equal to dou S by dou V at constant temperature, but the sign is going up. I'm considering as negative, so going down will be positive. So this is positive. Okay, if I take reciprocal of it, anyone can understand this? Okay, you have the document that I sent, right? Look at the answer in that.
Sir,
Yes,
here
sir.
both option A and
Sir,
D are incorrect, sir.
So I think there must be a changes in the question that indicate which of the following relation is correct. Then the option B will be the right one. Rest three are the wrong.
Oh, okay.
Yes, sir.
If we consider that which one is correct, then option B is correct, rather than
Oh,
A, C, and D are incorrect only.
okay. I actually I was reading it wrong. I was reading as which is correct only. Okay. Uh, Fine, then I will check it in the original question paper, June 2012, right? Okay,
Okay, sir.
okay. So I think that we did not discuss this type of questions based on Maxwell equation, probably. We have discussed other three. This one I look at, this is one of the tricks that I used to follow. So I look at it and we'll start our discussion tomorrow from this, and then we'll go to the temperature dependent or pressure dependent temperature changes. Okay.
Okay, sir.
Okay. So tomorrow will be some question discussions and majorly the theoretical part. Okay.
Sir, can you please explain that atom recombination?
Atom recombination also I will explain. I have the answer it. If you want, you can copy it Okay, but this is just simple discussion that is given. I will explain it in much detailed way. Okay, atom recombination. The hint is like for atom recombination reactions, the activation energy is zero. Why it is zero? And with a better pictorial representation, I will collect some information. Okay, here this simply the statement is only given. I try to find out the better pictorial representation, but due to insufficient time I could not do. But I will explain you in a clear way. I'm almost near to the answer, but to convince you, I need a better pictures. That's it. Okay.
Okay, sir.
Yeah. For the time being, you can, if you are using a mobile or something, you can take a screenshot or image of it.
Okay, sir.
Okay. So the remainings, I guess you can, you please try to solve all those questions. The questions that are given to you, we are discussing only CSIR net questions. There are also gate questions. You can have a look at it. Whenever you, whenever you require my help, you can approach me. Okay.
Okay, sir.
Here we finish our class. So with tomorrow, most probably I will try to finish the remaining topics of thermodynamics, and in the next session we will do molecular spectroscopy. That is the reason why I want to discuss as many questions as possible, because simply teaching theory does not clear you many things.
Okay, sir.
And see you tomorrow.
Thank you, sir.
Thank you.
Thank you so much, sir.
Thank you, sir.
Sir,
Yeah, please.
uh,